good morning. This is Monday morning, the 24th of October, 9:32 in the morning. Should be Calculus 2 class. The trouble is I'm the only person in the room. So we'll be starting from here. This was the last slide we did last time. This time we'll be, I'm sorry, we did that slide too. Hopefully we did anyway. Now we'll be starting with square roots of a general quadratic functions. This is the bottom of page 389 in the new edition, section 7.3. If you're in the old edition, probably a few pages off of there, but it's square roots of general quadratic functions. Okay. Now, how this begins is that so far we have dealt with expressions. Let me get my pen activated here. Okay. We've dealt with expressions such as the square root of x squared plus or minus a squared. Okay. And I would have written that slightly differently. They write it as two different ones. Square root of a squared minus x squared. Okay, so you can either have x squared plus a squared, x squared minus a squared, or a squared minus x squared, all under the square root. Okay, now, what if you had an expression like this? The square root of ax squared plus bx plus c. Well, with something like that, you can get it into one of those other forms by, and I know that all of you love and look forward to, completing the square, okay? And I don't know how much of a review you need of that, but let me just quickly go over what that would be, okay? If you had a form like this, and it's inside a radical, but I'm going to take it out to play with it, ax squared plus bx plus c. Now remember, the a can be positive or negative, the b can be positive or negative, c can be positive or negative. It can be any values in the world except a can't be 0. That's the only restriction here. If a were 0, that'd be a linear form, and you'd probably be able to do that. So we're just going to assume a is not 0. How do we mean by completing the square? Well, the first thing we would do would be divide everything by a, because it's really hard to complete a square if you have a coefficient there. So this becomes x squared, plus b over ax space plus c over a. Okay? Now why did I do the space there? Well, because we want to complete the square. And how do we do that? We take the coefficient of that linear term, that middle term there, and take half of it. So that would be, and here's what I'm going to do. On the next line, I'm going to write this as x plus b over 2a. That's what half of that is. Now, I'm doing a couple steps at once because I know it's how it's going to turn out. I know the end of the story. So you take that b over 2, half of b over a is b over 2a, and then you square it. That'd be plus b squared over 4a squared. Okay? And that is the perfect square of that. But I just added that to this, so I have to subtract it over here. Minus b squared over 4a squared. So, what does that produce? It produces a perfect squared, x plus b over 2a squared, plus, and if you put this over least common denominator, that would be 4a squared, that would be 4ca minus b squared over 4a squared. Now, you don't have to do that last step, but it just makes it a little easier to deal with. And sure enough, you could put 4ac. It doesn't matter which order you do it. That probably would make it be a little better looking. So let me do that. AC. It also be a little bit more familiar to you. Okay. And if you happen to remember, that's just exactly the reverse of b squared minus 4ac, which is the discriminant in your quadratic equation, quadratic formula. And your denominator is the square of your denominator in this quadratic formula, the square of 2a. So if that helps you remember, that's fine. But anyway, if all this was under the square root, then you have a form that's much more like this one. Only it's this quantity squared, x plus this, that could be your u squared plus, and then whatever that is. Even if it's not a perfect square, the square root of it is the square root of it. Yeah. So you could deal with that. So anyway, that's what you do when you have a quadratic in your denominator that's not of one of those other forms. So let's do example 6, which is completing the square. So I'm going to erase this stuff, and we'll do example 6. And I believe this is example 6 right here, so what I'll do is zoom in just so you can see it a little more clearly. Dx over x squared minus 6x plus 11 squared. Okay? Not exactly like what we had before, but it's close enough that we can fiddle with it. Okay? And here's how we're going to go about fiddling. Okay? We're going to complete the square for your denominator, x squared minus 6x plus 11. We want to complete the square. Well, there's no leading coefficient, or the leading coefficient is 1. So what I'm going to do to start with, if I had been thinking ahead, I would have already done it. Make a big blank here, because I want to get that plus 11 out by itself. Okay? Now, let's complete the square of the first two terms that have the x in it. How do we do that? Half of the linear coefficient, half of negative 6 is is minus 3. So right now we're going to write down x minus 3, because I know that's what it's going to turn out being. Take half of that as minus 3, square that, that's a plus 9. But you just added 9 here, so you got to subtract 9 over here so you don't change the form any. Okay? So this will be x minus 3 squared plus 2. And that's how they get the next step. Okay? This coefficient, this denominator that we had here is the same as x minus 3 squared plus 2. Okay? So from our original form here, this is equal to the integral. There she is.
Sorry, I'm ready.
No problem. All right, so this here. And I'll go and turn on the projector. And sitting here in the dark like a mushroom. If y'all want to hear. Okay. Actually, sometimes if it's too dark, I'll turn on this light, and then I'll flop them when you come in. Okay. Do you remember how to complete the square?
Complete the square?
Yeah. If you have a quadratic expression, how you complete the square and make it a perfect square plus or minus something else.
Yeah. Yes, sir.
Yeah, okay. That's what we're doing, and I've already gone over that. And I thought I turned on the projector, but evidently it didn't take. Let me try it again. Sometimes you have to hold it down just a little bit longer. I was sitting there waiting for it to come on, and it didn't. So it's on the way. Okay. Now, I completed the square for the generic form ax squared plus bx plus c, and I did that earlier. So if you need to see that when this gets on YouTube, look at the first part, and you'll see everything we did after before you came in. But then we went to example 6. This is the bottom of page 389. Okay, example 6, and this was the problem there. Okay, the integral of dx over x squared minus 6x plus 11. So what I did was take this quadratic form, x squared minus 6x plus 11, and I went to complete the square. Now, I do a little bit of a strange thing here that the book usually doesn't, but I find it easier for me to see. I write down the first two terms, the ones with x in them, x squared minus 6x, or those by themselves, leave a blank, and then write my plus 11. I mean, it's the same form. The reason I leave the blank is in completing the square, you're going to add something to that form. So to complete the square, you take, now, if this had an a here, if that had any coefficient other than 1, you divide each of these terms by that coefficient, okay? Okay, it doesn't, okay? So therefore, you're fine. So the next step, if you make that a 1, which it already was, take half of this one. What I do, I go and write down here, open parentheses, x minus, and then whatever half of this is, half of negative 6 is minus 3, and then I put it in parentheses and square it, okay, because I know that's the perfect square, okay, or the square binomial. So you take half of that, which is negative 3, square that, and that gives you a plus 9. That's why I left the blank here. But if I add 9, I've changed the form. I've changed the value. So I have to subtract 9 from the same line, so it keeps the value the same. So all I've added was 0, but I put a plus 9 there, minus 9 there. So that gets you to this form that we started with, this one right here. That becomes x minus 3 squared plus 2. Okay? And that's like one of the forms we were dealing with last week. Okay? Now, what you do with that then, this is just where I was, this thing here that we started with is exactly that. So what our integral is dx over, open parentheses, and then x minus 3 squared plus 2, close that outer parentheses, and square it. Okay, because you see, it was this thing in here squared. That's what the thing in there is, and you square that. All right. Now, at this point, notice they made a substitution. Okay? And they said let u equal x minus 3. Then du is dx. Okay? So now we have the integral from you don't have any limits on it, du, because your dx is du, and your u was x minus 3, so this is u squared plus 2 squared. And that's how they got there. They went straight from the form to that without telling you how they got there. Okay, so this is how they got there. Now what it's up to is us figure out how to integrate that. Okay. Well, that goes back to one of the forms like we did before. What was our technique for that? If you had, now before we had radicals down here, this one's a square down here. Same type thing. What was your substitution that you would use to solve something like that? Second? Actually, I believe it was tangent. Okay? And let me, you see, here he is. Marcus is here. All right. Now, we started on page 389. In fact, we haven't gotten off 389 yet. We're still there. This is example 6, bottom of that page. And we started with this form, okay? And this wasn't a particularly attractive form. That was a quadratic in the denominator, not one of our sort of standard ones we can use for our trig substitutions. So what we did was complete the square on this, and that's what we did up here. Move that 11 far out, and just take the two terms with the x in them. If this one had a coefficient in front of it, divide that out, okay? It didn't. It had a 1 there, so we're happy. So what we do is take half of the linear coefficient, half of -6 is -3. What I do, I go and write down, because I know this is what it's going to be, as long as that coefficient is 1, open parentheses, x -3 squared. That's what this is going to become. So I take that -3 squared, that becomes a +9. This is the perfect square trinomial of that binomial squared, okay? We already had the +11 here. That was in the original problem. But as soon as you add 9 here, you've changed the expression. So what you have to do to keep it the same is subtract 9 from it. And now it's the same expression it was before. It just looks a lot different. Well, this is your perfect square, x -3 squared, and this becomes +2. So the next thing I did was then plug that in, the integral dx, and this thing here, which is what we started with, becomes that x -3 squared +2, and then you take that, take that and square it. So you get that. So now they did the substitution, let u equal x -3, then du is dx. So now this becomes du over u squared +2 squared. All right. Now, that's a form that maybe on first glance you might think you might be able to do another substitution. Not a regular substitution, like u equals something. That won't work, or v, or whatever you want to call it. But this is more like our trig substitutions we did before. Okay, and the question was, what's this a trig substitution of? And that, I think, is going to be tangent. So let u equal, actually, here's how she say it. I'm using the wrong pen. Okay, how we did that was now let u equal to, now it was when this was a squared. Well, that's not a perfect square anymore, so that's going to be the square root of 2 times tangent theta. That's going to be our next substitution. Now this is, you're changing to thetas, so then du is equal to what? It's derivative of tangent theta. Square root of 2 times, remember what derivative of tangent theta is? If you have forgotten, flip to the back of the book, not the integral part, but the differentiation part. Find your trig substitution, derivative of tangent x is before your integrals, yeah, the page before the integrals. Flip one more page back. One more page toward the front. That, differentiation, trig functions, number 15. Secant squared x. So this will be, du would be square root of 2 times secant squared theta d theta. We're writing in differential form. Okay, so now we take this, that's our du, so our new integral is going to be, I'm going to take the square root of 2 on the outside, secant squared theta d theta. That's your numerator with the square root of 2 on the outside. your denominator is it's the square root of 2 squared times tangent squared, so that would be 2 tangent squared theta plus 2, right? And that whole thing is squared, right? Okay. So what we're going to do here is the square root of 2 times the integral secant squared theta d theta. What I'm going to do is take that, factor out basically a square root of 2. Well, no. Let me, to save writing, what I'm going to do here is call this 2 times tangent squared theta plus 1. And what is tangent squared theta plus 1? Secant squared theta. So this will be 2 secant squared theta, okay? And then we're going to square it because that's what your denominator was. So that's going to be, I'm sorry, the 2 squared is going to be 4, so the 4 is going to come out here, okay? And that's going to leave you secant squared squared, which is secant to the 4th theta in your denominator, okay? Which, by the way, is, you can leave that square root of 2 over 4 if you want to. You could do other things with it, but I don't see anything wrong with that. And this would be d theta over secant squared theta. But what is secant squared, 1 over secant squared theta? Cosine squared theta. So it's square root of 2 over 4 times the integral of cosine squared theta d theta. Now, I don't know if you remember how we did that before, but if you don't remember, go back to your tables at the back of the book, okay? Now we're going to stay with the integration tables, and we want the trigonometric forms. And there is, number 35 is integral of cosine squared u du, right? So this is going to be simply the square root of 2 over 4, okay? And this integral of cosine squared u du is going to be 1/2, and they have a u, we have a theta, so let's just change it to theta, plus 1/4, and they have a sine 2u, we'll call it sine 2 theta, okay, and then plus c. Okay, so if we multiply through our coefficient in front, that would be a square root of 2 over 8 theta. Theta, can't write, plus square root of 2 over 16 sine 2 theta plus c. It may not be the same c we had before because we multiplied by it, but still it does. Okay, now that's one way to write the answer. That's not the only. Let's see what they did. They may have to do something else to it. Yes, they did it slightly differently, okay? And I think it's important to. They gave you this one in sine 2 theta. But do you remember what sine 2 theta is? Does anyone remember? Sine of 2 theta. Okay, that's in the front of your book. If you go to the front of your book, that cardstock page in front that says algebra on the front side and trigonometry on the back side. And if you go to your double angle formula there, sine of 2x is 2 sine x cosine x. So I think that's the form we ought to use. So instead of sine 2 theta, we'll put 2, which is going to change that 16 to an 8, sine theta cosine theta. Now here's why we did that. Okay. I'm going to erase this up here because I need the space. Okay. All right. Here's why. Because you know we still got to get back to our original variable, which is x, okay? And we had u equal square root of 2 times tan theta. So we need these in terms of theta, not tan theta. Well, first, and this is hard to read, so let me clean that up a little. Yuck, it didn't clean. Okay. Goodness gracious. Okay. This is a theta here. First thing we need is what is theta. From this, we see that theta is equal to 1 over root 2. Okay. Let me back off and do it. I was doing too many steps, perhaps. Okay. Let's solve this for theta. Okay. First thing, you divide both sides by root 2. So you have u over root 2 is equal to tangent theta, right? And then take the inverse tangent. So inverse tangent of u over root 2 okay, that's what theta is equal to. Okay. Now, that's a little messy, okay? But that's what we need for this theta, an inverse tangent. So remember that. Let's not use that for sine and cosine, okay? Here's what we use instead. As soon as you have this, that tangent theta is equal to u over root 2, draw your little triangle. We love these, don't we? Yes, okay? There's your right angle. This is your angle theta, right? Now, okay? The tangent of that angle theta is what? Opposite over adjacent. So that makes the opposite u and the adjacent root 2, doesn't it? Okay, what does that make the third side, the hypotenuse? Okay, so this up here would be u squared plus 2. Square root of that. Okay, square root of that, right. Okay, so now we can figure out what sine theta is, because this theta is the same as that theta. So sine theta would be okay. Sine theta would be u over the square root of u squared plus 2, wouldn't it be? Opposite over hypotenuse. And cosine theta, sorry I don't have room to write, is equal to square root of 2 over that. The square root of 2 over the square root of u squared plus 2. Yeah, this thing is aggravating. There we go. Okay. Now, I'm going to have to erase some stuff so I have room to write. So I think we're through with this up here for now. I don't think we need that anymore. We've already, goodness gracious, this won't erase. There we go. All right. I sure hope we don't need that anymore. So what our solution is, that integral that we started off with is the square root of 2 over 8 times, and that theta was, from up here, inverse tangent of u over root 2. Okay? Plus root 2 over 8. Okay, that's down at the bottom. Sine theta, which is u over the square root of u squared plus 2 times cosine theta, which is the square root of 2 times the square over the square root of u squared plus 2. Yuck. All right. It went too far. Okay. Plus c. Okay. Don't forget your plus c. Okay. We can simplify that. Okay. Not too much, but a little bit. I'm real tempted to pull out the root 2 over 8 for now, I'm going to deal with it later, but not yet. Root 2 over 8 times inverse tangent of u over root 2. It's aggravating. Okay. Plus, I pulled out that. No, goodness gracious. All right. This now is the root 2 over 8 went on the outside, and this is u times root 2 over, but those two denominators are the same, multiply to each other, lose the square root, that be u squared plus 2. Okay? And then you have your plus c. Okay? Now, I need some more room. So what I'm going to do is erase. I think we're through with our triangle now, aren't we? Okay, so let's get rid of that, because it was very useful, but it's in the way now. And we already got what sine theta was, so I don't think we need that anymore. Okay, this was all part of that triangle deal. And I think we've also used what? I think we've already used what theta is, so I don't think we need that anymore. Okay, and that was that too. And that. I think we got rid of, we're through with this too. I'm probably doing too much, but I can't get it to erase anyway. All right. That's all we're going to deal with now. So that got us from our thetas to our u's. Now let's use this to get from u's to x's. All right. So this will be, all right, the square root of 2 over 8. The inverse tangent of, instead of u, we'll do x minus 3 over root 2, okay, plus, okay, the u is x minus 3 times root 2, so let's do the root 2 times x minus 3. I swear, this is such a pain in the neck. Okay. Okay, over x squared plus 2, which is our x minus 3 squared plus 2. But if you'll think about that, and I think I did erase, no, I probably did erase too much. That's exactly what we had here. X squared plus minus 3 over, plus, okay, plus 2. That was exactly what we had before as our original denominator, okay, which I've already erased. I knew I was going to regret that. X squared minus 6x plus 11. So this is x squared minus 6x plus 11. Okay. All right, all that plus c.
And it has to be squared, alright?
What's that?
X squared minus 6x plus 11 has to be squared.
Okay. No. Remember, in the original thing it was, but we let u equal x minus 3, so
Yeah.
like this isn't squared. If that were squared, it would be.
Okay.
Okay. So we're just got that. Okay. I sure hope that's going to be the answer. Let's see. Boy, we're gonna leave. Oh, here we go. Okay. So what we have is the final answer. Now they, for some reason, choose to write rather than the square root of 2 over 8. They write this as 1 over 4 root 2. Which most of the time you try to get the radicals out of the denominator. Here they moved it into the denominator because that 8 is 4 times 2. 2 is square root of 2 times square root of 2, so you cancel one of those out. So that gives you that. That's no problem with that. Why they do it, I'm not sure, but they do. And then the next part is the inverse tangent of u over root 2. Why did they leave the u in? Oh, no. They go back to the bottom. Okay. I was skipping. Inverse tangent of x minus 3 over root 2. That's fine. Inverse tangent of x minus 3. Sorry. It's going to write incorrectly later. Okay. X minus 3 over root 2. Okay, that part is good. And then they have now oh, I see what they did. They didn't put the, okay, sorry about this. Okay. They didn't put this, yuck. I go to do this and it doesn't take, okay. They leave that as a coefficient there and multiply that through here too. When you do 1 over 4 root 2, that's what this is, then the root 2's cancel out and this gives you plus x minus 3 over 4 times x squared minus 6x plus 11. And then that plus c. Yes. So we got the same thing they did finally when we manipulate our forms around there to do it. That does give us the same thing. Okay? Now, where you put the radicals, that's up to you. I guess since they wound up with the radical in here, they say, well, it's in the denominator anyway, so put it in the denominator there. That's fine. And that way, if it's in the denominator there, it wipes it out of the numerator there. So that gives you a so when you deal with calculus and integration and stuff like this, there are probably 5, 6, 7 different ways to write the perfectly same correct answer. It just depends on how you do it. And that's why, for one reason, I don't like these computerized packages that are only looking for one answer. and let's say you have 3 opportunities to get the right answer. You've got the right answer, but you have 3 opportunities to get it into the form that want it, and you don't know what that form is, so you might try it, run out of time, and you still get not the form they want, and it's still the right answer. But what's even worse, you might doubt yourself and think your answer's wrong because they told you it was, when it is perfectly right. You go back and change something in the problem, and then you're in a terrible mess. So frankly, for calculus, I've never seen one of those packages that really worked all that well. So anyway, that's my little bias. I'll get off my soapbox and move on to that. That's the end of 7.3. Any questions? Okay. Do you want to do the preliminary exercises? Okay. Well, let's just see. They do have some more slides here, and it's some of the stuff we did. So let's go and recognize them. Okay, we started with that. The next slide they did is what our trig substitution was. Yep. Which is exactly what we did. We let your u equals the square root of 2 times tangent theta. And the square root of u squared. So basically you square this and that gives you 2 tangent squared theta plus 2. Factor out the square root of 2 and that leaves you the square root of tangent squared theta plus 1. That's secant theta, square root of secant squared theta. So it's secant theta. Du then would be 2 secant squared theta d theta. They did it in a different order that we did. Square root of 2 secant. Okay. Then your integral here would be the du becomes square root of 2 secant squared theta d theta. Your u squared plus 2, which we have here, that would be 2 secant squared theta. Okay. And then you square that, that gives you 4 secant squared, secant fourth theta d theta, exactly like we did. Now what they did differently from what we did, I wrote this as square root of 2 over 4. They wrote it as 1 over 2 root 2. No problem. And then we already did this 1 over secant squared times secant squared is cosine squared. And then they did the same thing we did, look in the back, and got the thing, except they didn't write it in sine 2 theta, they wrote it in this form, which is perfectly fine. And now you can factor out another 2, which gives you a 4 over here, and let's see where they go from there. They don't go much further, I don't think. What they didn't go to is our triangle, just like we did. Okay, so they think along similar lines. Okay, and they wrote the theta, and we knew that the tangent of theta was u over root 2. We knew that from our substitution, so that means this has to be the square root of u squared plus 2, which is exactly what you got. And when you plug that in for your sine theta and your cosine theta, that gives the term, and they're skipping lots of steps, but you can see they got the same thing we did. This is from our theta, and this is from our, and they pulled out that coefficient, and this is from the sine theta, cosine theta, so the denominators, which are square roots before, now becomes this, and that gives you a numerator, got your plus c, and then they multiply this back through, okay, and that would be 1 over 4 root 2 inverse tangent u over root 2, plus, and when you multiply this by that, these go out, and that gives you u over 4 times square root of u squared plus 2, plus c. That gets you to u. Now you go to x, and using the next they don't even show you how to do that. Not on the slides. They did in the book, but not on the slide. And then these are in the summary. See, these slides, I think, what? Who decided what was going to be on a slide or not? It's so helter-skelter here. Here are your trig forms. And guess what? You really don't need the square roots there anyway. But you can have them there if you want to. But basically, the identity used when you have this form is x equal a sine theta. Okay? Now, if this didn't have the square, it would be x equal square root of a sine theta. Okay? So that's your substitution here. So this becomes a squared minus a squared sine squared theta, which would be a squared times 1 minus sine squared theta, which is cosine squared theta. Square root of that would be a cosine theta. Derivative of this would be a cosine theta d theta, and your square root would then be a cosine theta, which I just did. Okay. This is your tangent substitution. X equal a tangent theta. Okay. And another way you can write that. Excuse me. This thing becomes a secant theta, just like we did in the last problem. The derivative of that would be a secant squared theta d theta, and then you get a form that you can fiddle with. This form, you use the x equal a secant theta, because secant theta minus 1 would be tangent theta, so that becomes a tangent theta, and dx would be a secant theta tangent theta d theta. So whether you have the square root or not, you still make those substitutions. If you have one of those forms, still make the substitution. That stays the same, that stays the same. Only thing that would differ would be this side and that side. You just have squares rather than square roots. Okay. All right. Now, when you do make your substitutions, this is review here. When you do make those substitutions we were talking about, okay, remember this form here is a sine theta. When you put your theta in here, that makes, if x equal a sine theta, that means sine theta is equal to x over a, so sine of theta would be x over a. That makes this one down here the square root of a squared minus x squared, which is exactly what your original form was, okay? Same thing here with this. If this is what you were given, your substitution is a tangent theta divided by a tangent theta is x over a. That means the x is here, the a is here. This is what we did on the last one. That makes this up here the square root of x squared plus a squared. And when you had your this form, you say let x equal a secant theta, because secant squared minus 1 is tangent. So then, excuse me, secant theta is, sorry, x over a, well, secant is hypotenuse over adjacent, because it's the inverse of the cosine, which is adjacent over hypotenuse. So this would be x over a, and that would be the square root of x minus a squared. So these triangles are very, very helpful, especially if one of your answers comes out to some other trig function of theta. Then the triangle can tell you exactly what relationship that is, as in when we did that and had a sine in our answer. This sine is this over that, cosine would be this over that. So I think we're using that. That's what we're using. But you see, if you have those in your answers, you can do your substitution back here without having to go through anything too complicated. Use your triangles to tell you what those are. I think that's the last slide. Yes, it is. Okay, so let's scoot back one and let's look at your preliminary questions. I don't know why my head's clogging up so badly. State the trig substitution appropriate to the given integral. Okay, here's the first integral, the A integral for preliminary question 1. Okay, this integral is the square root of 9 minus x squared dx. What trig substitution would you use for that? Okay, and what do you say? Let u no, okay. Here's the difference. With the trig substitution, Yeah, it's let x equal. Even though that's part of the problem, the trig substitution worked this way. Let x equal what you say? Yes, but it's 3 sine theta. That's it. X equals 3 sine theta. That's all they need for this one. You can carry it further if you want to, but that would be that one. The B one here, this integral would be the integral of x squared, x minus 16, x squared minus 16 squared, not to the 3 halves, sorry about that, dx, okay? It doesn't matter where it is and what form it is or anything else, what your trig substitution do. Okay, let x equal 4, you said it, secant theta. That would be your trig substitution, okay? Because 4 squared, 16, secant squared minus 16, factor out the 16, secant squared minus 1 is tangent squared. That's what you want, okay? Let's go down to this one. C is the integral of x squared. It doesn't matter what these other things are. X squared plus 16, and that was to the 3 halves power dx. What would be your trig substitution here? Okay, let what? X equal 4 tangent theta. Done. Excellent. D. That integral is the integral of x minus 5. I'm sorry, x squared minus 5 to the minus 2 dx. What trig substitution do you have here? Let, say again, x equal, it's not a perfect square, except it is a perfect square of what? Irrational number. The square root of 5. Yeah, it's x equals the square root of 5 times, and what you say, secant theta. There it is. Okay? Now, I think that's all they wanted. They just said state and trigonometric substitution appropriate. Okay? So I've got to find where we are in the back of the book. I think we're right here. This is 7.3 preliminary questions. The A is x equal 3 sine theta. B is x equal 4 secant theta. C is x equal 4 tangent theta. And D is x equals square root of 5 secant theta. Good deal. Now, I don't think number 2's in the back for some reason, but let's see if we can do it. All right, to erase those? Okay. You see the pattern of what your trig substitution should be. And you work out the rest of it and see what comes out. That's your pattern. Here's number 2 of these preliminary questions. Is trigonometric substitution needed to evaluate this integral? The integral of x times the square root of 9 minus x squared dx. Second, you certainly could. The question is it necessary? Get too wrapped up in this. If I had asked you this question a week ago, how you do that, what would have been your answer? what substitution? You wouldn't use the trig substitution. You'd say let u equal 9 minus x squared, wouldn't you? Right? And then du would be minus 2x dx. Well, there you have it, x dx minus 2 just, yeah. You could do that one just with a plain substitution. Because basically the derivative of this is almost already there. You see, the ones we were doing before, those derivatives weren't there, okay? You either had x squared out here, or you didn't have anything out here, or something that you couldn't do without, okay? Then the trig substitution works. But when the derivative of this is already out there, do it, okay? Don't make up a trig substitution. You're going to get in a hairy mess by doing that. It should work, but it will be a lot more work. Always try to be lazy, do the least work possible, okay? So that answer would have been a no, but I don't think they have that answer in the back. Yeah, they don't have the evens for some reason. All right, number 3, express sine of 2 theta in terms of x equal sine theta. ITO is in terms of x equal sine theta. So we want it in terms of x, where x is equal to that. So we want to express sine of 2 theta in terms of x. What's the first thing you better do? You don't want that 2 theta in there, you want just theta. Right? So how do you do sine 2 theta? What is that equal to? We looked it up earlier. 2 sine theta cosine theta. Very good. Now what would we do with that x so we can express that sine 2 theta, which is 2 sine theta cosine theta, in terms of x? Well, guess what? I could do part of it right now. This would be 2x, because that's what sine theta is, but now I've still got a cosine theta. I need to get that cosine theta in terms of x. Did you finish? Okay. Wednesday, yeah, you can do it right after class. Okay. All right, good deal. Thank you. Let's see what, okay. Try to remember to get the key for that later. Okay. Well, I can deal with sine theta, that's x. How do I deal with cosine theta? It's no coincidence that those triangles are there, are they? Oh, yeah. Okay. Rewrite. Well, you don't have to rewrite anything. Draw your little triangle. Use a different one because I don't like to draw my own. Here's my triangle. Let this be theta. And if sine theta is equal to x, what does that mean? Say again? Yeah, hypotenuse, no. The opposite will be x, hypotenuse 1, because it's x over 1, isn't it? Isn't x over 1? And sine is opposite over hypotenuse, so that would be x over 1. Now you can tell me what the other side is, because cosine is going to be the adjacent over 1, right? What is the adjacent side then? Take the square root of that. You got it. So this would then be 2x, because sine theta is equal to x, times, what's cosine theta? The square root of 1 minus x squared over 1, but I'll leave off that. Okay? There you have it. That is what sine 2 theta is equal to that in terms of x, where x is sine theta. Okay? They better have that answer in the back, otherwise I'm going to shoot the author. No, I'm not. 2x times the square root of 1 minus x squared. Very good. And number 4, they don't have it in the back. Draw a triangle that would be used together with the substitution x equal 3 secant theta. If that was going to be my substitution, what would be my triangle? All the triangles look the same, and I always put the theta in the same place, but where do I put the rest of it? First thing I would do, divide both sides by 3. So secant theta is equal to x over 3. What does that mean? X is the hypotenuse this time, and 3 is adjacent this time, because secant theta is 1 over cosine. Cosine is adjacent over hypotenuse, so this would be hypotenuse over adjacent, so that would be x over 3. We still got one more thing to write. The square root of x squared minus 9. There's your other side. Now you can get any trig function out of that you want, right? Good deal. They didn't have that one in the back either, I don't think. I didn't see it before. It's still not there. Okay. Homework exercises. I would definitely do. Light in my eyes just really bothers me. I would do 1 and or 3. Okay? Then I would do any of the odds, 5 through 9, 11 and or 13. Excuse me. Oh, my throat's hurting. I don't know why. What's that? Yeah. Right. Any of the odds, 15 to 31. Right. Wait, I lost 33. There it is, 33 at the bottom. Either 33 or 35, or both. Any of the odds, 37 to 41. I think we didn't do those. These are the new ones. Any of the odds, 37 to 41. Either 43 or 45, or both. And then any of the odds, 47 through 53. Okay? And they do give further insights and challenges. If you're interested, you can pursue that, but I will let that be up to you. My eyes are doing weird things over me. I think I've been staring into that light too much. Sometimes when they do this, it means I may have a migraine or like headache coming on. I hope that's not the case today. Ugh. All right, 7-4. I can't remember what your majors are. Do you know if you're going to use hyperbolic functions in them? Don't know. What is your major? Chemical engineering. I'm guessing not. What's yours? Mechanical. I don't know about mechanical. I can't imagine too many of this. Frankly, I really don't care for them because, let me just confess this. I learned hyperbolic functions in calculus. Use them in calculus. I don't think I ever use them anywhere else. Okay? Now, I'm not saying there's not a use for them. Someone out there must use them or else they wouldn't teach it. But if you define the hyperbolic functions, and then on your page 393 or thereabouts, whatever that is, it shows you what those are. Hyperbolic sine is x, e to the x minus e to the minus x over 2. Hyperbolic cosine is e to the x plus e to the minus x over 2. And then you can fiddle around with those and do your your other identities, and to me, they're close enough to sines, cosine, the trig functions, but just a little difference, and that little difference throws me off every time. Because do I put the minus here, sign here, or there, or not, or where, or, So that's why I don't like to mess with them. If you go back and use the exponential forms, which is not that difficult, then you can do it without ever going to the hyperbolics. So that's what personally I do. So I'm willing to skip this section unless y'all are up in arms and say, no, we want to do it. Okay, you're not? Wow, I'm surprised. Okay, so let's skip 7.4. Sometimes I do, in fact, I guess it wouldn't hurt. I'm going to do this as quickly as possible, just so you'll see it, but you're not responsible for it. Let me just go through these really, really quickly, okay? So if you ever need them, you've seen them before, you can look them up in a table and go with them, okay? I show from current slide. Okay. Here are your hyperbolic integral formulas, okay? I don't suggest or even recommend you do anything, but if you like memorizing them and it's easy to do, they're very simple. They're just like the trig functions, except sometimes the sign changes, sometimes it doesn't, right? Integral of sine would be minus cosine. Here it's plus. Integral of cosine would be sine. It is hyperbolic, so that is the same. Integral of this one is tangent. That's the same as it would be in trig. That would be the same as it would be in trig. These, however, this would be a minus. No, this would be a plus here. Now it's a minus. That would have been a minus already. So when it gets down to it, what changes here is from trig, that would have been a minus, is now a plus. That would be the same. That would be the same. That would be the same. This would have been a plus here, and now it's a minus. And that's nice. I mean, it's close enough, not the same, and it blows my mind trying to remember. So if I go back to the e to the something, it all works out. I don't even have to mess with that. So unless you need it, if you need it, there they are. If you don't need it, I say don't worry with it. Okay? Now, therefore, with those functions in mind, your substitutions, but why would you do it? You already have a substitution for this. This would be x equal a tangent theta. Why do hyperbolics when tangents will work perfectly well? Okay? This one, you would have done a secant theta. Why go and do a hyperbolic when this would work perfectly well? So, I don't know. I mean, frankly, I can't answer the questions, why do they do it? I don't know. We already have a thing that would do it. Why mess with hyperbolics? Okay? I'm biased, obviously. Okay? Now, this is part of a problem. I'll let you look at it, play with it, do whatever you want to, but I'm not going through the problem. All right. So here's your, basically, exactly what we just did before. You saw every one of these. They just now put them in a theorem. Oh, I'm sorry, no. Okay, so yeah, this is doing the very ones we would do for a trig substitution. Now they're showing what your hyperbolics. Why? I like trig substitution. I'm going to be staying with them. I wouldn't even mess with these. The only ones that might be a little different, might be, but I still think you could do it, would be this one and that one. To me, it's just not worth it. If you do use hyperbolics, most of the time it's going to be hyperbolic sine, cosine, and tangent. When are you ever going to use hyperbolic secant and hyperbolic cosecant? I don't know, so I wouldn't mess with it. But if you need it, there it is. Okay? Now, this is something worth looking at because, by the way, remember there are papers due in this class, right? Okay? Here is somebody you might choose to write on. Leonard Euler, one of the, and it looks like it's Euler. I used to call it Euler until I saw a book that said, no, it's pronounced Euler, like the Houston Oilers, but they don't exist anymore. Okay? He ranks among the greatest mathematicians of all time. He was a really handsome character too, by the way. Okay? So his work printed in more than 70 volumes. Now just think of that. His work would take 70 volumes to print. This was before word processing. I mean, it was all done, frankly, probably all done in Latin. Okay? At least most of the scientific writing was done. It's incredible that one person could produce that much. It contains fundamental contributions to almost every aspect of mathematics and physics of his time. Now, he came along after Newton, so he built on Newton's work and stuff. The French mathematician, here's another potential topic. Who in the world is Pierre-Simon de Laplace? Okay? He once declared, read Euler, he is our master in everything. Okay? Laplace did Laplacians, he did a lot of stuff himself. So anyway, incredible character.
For the paper, we can write about person.
A person, a theory, of application. You choose anything that would show up anywhere in here.
You said like 1 to 2 pages or
1 to 2 pages of double space word process text. And what? Do what? That's fine. You can use any format you want to. Just be consistent about your format. Yeah. I'll accept any of them. Because some majors like to use PSA, Psychological Society of America. Or APA, that's APA, American Psychological Association. And the reason they showed Euler here, and I'm not entirely sure why it shows up in this section as opposed to somewhere else, but this is, okay, this is where it's coming from, okay? There's a differential equation that does show up in nature sometimes. Now, obviously one solution would be e to the x, right? Because that would work. But e to the minus x would also work. And any combination of e to the x and e to the minus x, which would be your hyperbolics, okay? Those would also work. So that's probably why it's showing up here. If you had this function, then you would probably use sine or cosine, right? Because the derivative of sine would be cosine, the derivative of cosine would be minus sine, so the second derivative of y would be minus y. So this would be using a solution there would be sine or cosine or any linear combination of those. This isn't differential equation, so we shouldn't really be doing this too much. But, and here is where they show that very thing. Here would be your answer for that, any linear combination of sines and cosines. Okay? That would work for that previous one. Okay? Wouldn't for the first one, but it would for the second one. All right. Now, here's something I think all of you know. I is equal to e to the minus, the square root of minus 1, right? Okay. That's your imaginary unit. They call it sometimes. I. Okay. As opposed to the x-axis. Don't confuse that. Okay. Now, here is something else, okay? And this is where Euler comes in. He started playing around with this and found that he can express that same he can express a linear combination of sine and cosine as e to the it. Okay. Now, what you would have to do is play around with that, but believe it or not, that is indeed true. I think I've already. Okay. Now, I think this is another one of Euler's discoveries, is that e to the it is cosine t plus I sine t. Okay? Now, some of you in some of your fields may run into this. I'm guessing maybe a little bit more mechanical than chemical, but I don't know that much about chemical engineering. It just doesn't look very chemical to me. Okay. But you may run into it in statics or dynamics or somewhere like that everybody would take. But here is what I'm getting at. Okay. This is one of the most incredible equations of all time, I think. And this is true. E to the I pi is equal to -1. This is, oh, and by the way, where do we get the E for the, why do we name that as the base for our natural system? E from Euler. He's the one that came up with the symbol E, representing the base for our natural number system. We think of it as base 10. In arithmetic, base 10 is our base. But when you get to calculus, E is our base, because you integrate E, you get E. You differentiate E, you get E. E is the natural base for our number system. But it's an irrational number. 2.71, blah, 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 blah. It's irrational. The other most famous irrational number is pi. We know what that is, ratio of circumference to the diameter of a circle, and that's 3.14159, blah, 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 blah. It's an irrational number. And then little I is your imaginary unit. So these three, the two most common irrational numbers, and your imaginary number, put together in this way, they're equal to -1. This was another one of Euler's discoveries. Incredibly simple thing. Now, by the way, I may not have remembered to say this at the beginning of the term. There is a book in the library, or at least it was in the library, because I donated it to the library. It was a book named The Math Book. That's the title of it, The Math Book. It's written by a guy, goodness, I can't think of his last name now. It's an unusual last name. I think of Barbara Kingsolver. That's not who wrote this one, but it's a name as complicated or strange as her last name. It's something else like that. It's not Kingsolver, but it's a strange last name like that. And that book is 250 of the greatest discoveries ever in mathematics. It sounds sort of okay, except that he had a one-page write-up on each one of those, and the opposite page is a beautiful illustration of it. It's just incredible. There's probably a bunch of things on prime numbers in there. This shows up there. Euler himself shows up there. Maybe some of those other equations do. And then there's applications of it. So it is simple. One page of text, one beautiful picture. So if you want to look there for a paper topic relating to some of this stuff we've done, it's there. I'm pretty sure that equation is there. And he writes up about it. So it's pretty incredible. It's amazing, in fact. Okay? That simple of a formula. Okay. And that was the section you're not responsible for, but I did want to mention Euler and those incredibly simple but incredibly complex formulas at the end. which really have not much of anything to do with hyperbolics, but they're stuck in that section, so I did want to do it. And that last one is Euler's formula, or a couple of those, and he makes, there's some other, it's well worth the read, that portion, and then they go back and do some hyperbolic with it too, but who cares about the hyperbolic? I'm sorry, I'm biased, okay? All right, let's move on to 7.5. On your test, you won't have any hyperbolics. If you do, it's my fault. I didn't mean to put them there. I can't get 7.5 to come up. Okay, here we go. All right. Now this sort of jumps in the middle of things. We're going to back up a little bit from there. Okay. Next, and by the way, remember the title of this chapter, Techniques of Integration. Okay, and basically what we did, we had earlier done substitution, okay, and then we sort of did a few more substitution-like things. Then we did things with trigonometric integrals, and then we did trigonometric substitutions, and now we're doing one more method, and this is called the method of partial fractions. Now, this is used specifically when you're integrating what they call rational functions. And someone remind me what a rational function is. Let me get my pen back. Okay, a rational function. Okay, it's the first 5 letters of rational. Ratio, which means division. Okay, what a rational function is a function that is the ratio or division of two polynomial functions. Let's call it P divided by Q. Okay, and we'll make both of those as a function of the variable x. Okay, P of x divided by Q of x. Yeah, wow, am I putting zeros in there? I don't know. Okay, P of x divided by Q of x. Now, here are the criteria for using method of partial fractions. The idea is to write f as a sum of simpler rational functions that can be integrated directly. That's what we're going to try. For example, let's start with something pretty simple. Now, why they don't say this to begin with, but I'm going to go and say it to begin with. If it's a ratio of P over Q, they're both functions of x, polynomial functions. What's required is that P be of degree less than Q. If it's not, then you do long division. If P is greater degree than Q, divide Q into P, and you're going to get a polynomial plus some form of P over Q where the P is less degree than a lower degree than Q. So I wish they'd have said that right out front. It seems like to me it needs to be said. Okay? So you might first have to do long division to make sure that the degree of P is less than the degree of Q. The other requirement is they need not to have any factors in common. So if P is factorable and Q is factorable and they have some common factor, get rid of it. Okay, we don't want that messing up the picture. So once that's gotten rid of and you got P over Q, where P is degree less than Q, and there are no common factors, then you proceed as they tell here. Okay, they're going to come at the end and hit you with all that later. I think they should hit you with it to begin with. Okay, so let's do an example. Is this a rational function? 1 over x squared minus 1. Sure enough, a A polynomial can be just a single number, like 1, okay? So that's a polynomial function, and certainly x squared minus 1 is a polynomial function. And the degree of the top one is 0, the degree of the bottom is 2. Back to x one, okay? So the degree is less, so we can proceed. Okay, if you're trying to integrate that, of course you might try one of the substitutions we just had. That may be a little complicated. If they're strictly polynomial forms with no radicals in them and stuff like that, sometimes it's easier to use partial fractions than doing some things like we just did, okay? If you got radicals, you got to use the trig substitution. If you don't have radicals and they're all polynomials, use this one. So what we do, we see if we can factor that denominator. Can we? Sure we can, can't we? Okay, that would be x how do you factor x squared minus 1? X plus 1 times x minus 1. I know it's a long time ago, but you remember doing that, right? Now, okay, notice that that is a numerator over a product of two things in the denominator. What we're hoping is you could break that into, and by the way, if you tried to integrate this, there's nothing we've done so far except maybe a trig substitution, which is a little awkward, to integrate that. You can't do any other kind of substitution, but this method will give you another tool. What we're hoping is there's some way you could split this compound fraction, you might say, into two simpler fractions. A over x plus 1 plus b over x minus 1. Okay? Now I'll take you through the long way, and then I'll come back and show you a shortcut. Okay? The long way would be, well, let's change this back and try to get what we had to begin with. Okay? Now, what you need first is, this is sum of two fractional forms. You need the least common denominator. Well, that's going to be the product of the two. So the first here you'd have to multiply by x minus 1. But if you multiply the denominator by that, you have to multiply the numerator by x minus 1. This one you multiply the denominator by x plus 1. But if you do that, you have to multiply the numerator by x plus 1. Okay? Would you? Okay? Now, let's add those together. Because they have the same denominator, you can do x plus 1 times x minus 1, right? Which, by the way, is x squared minus 1. So that gets you back to what you had to begin with. But this is ax minus a plus bx plus b, right? Now, if that's supposed to equal that, that means that ax plus bx is equal to 0, because there is no x term over here, right? Would you agree with that? And that minus a plus b is equal to 1, because that's a constant term there. So this is made up of two terms. A plus b times x. There is no x there, so that has to equal 0. So just leave the x's out of it, factor out the x. They don't need to be there. Right. But a minus a plus b is equal to 1. Well, let's go with that bottom one and say that that tells you that b is equal to a, right? And the top one would then tell you that, it doesn't matter what order, 2a is equal to 0. If b is equal to a, then you could write A plus A is equal to 0. So I've done this backwards. Sorry about that. Let me back off. I messed things up there. Okay. Let's do the top one first. Okay. The top one tells us that A is equal to minus B. And the bottom one says that 2
So the top one doesn't have A's.
yeah. Okay. Let me start this whole thing over. I keep seeing easier ways to do it. Okay. The easiest way to do this, add the two equations together, right? That goes out, and this will be 2b is equal to 1, b is equal to 1/2. Okay? Then the top equation tells you that a is equal to minus b, right? So if b is 1/2, a is equal to negative 1/2. So now we have our answer here. This 1 over x minus 1 squared would be a minus 1/2 over x plus 1 plus 1/2 times 1. Yeah, let me write them the same way. I decided midway I wanted to change them, and that really wasn't fair to do. Okay. Okay. Plus 1/2 over x minus 1. Okay? So that this integral could now be written as minus 1/2 the integral of dx over x plus 1 plus 1/2 the integral of dx over x minus 1. If this original form was an integral here, then you write it like this. And we know what this integral is, don't we? Do we?
What'd you say?
What that integral is. Isn't that a natural log?
Yeah.
Natural log of x plus 1. And that's a natural log of x minus 1. So what we have is minus 1/2 the natural log of x plus 1. I put them in absolute values. Plus 1/2 times the natural log of x minus 1. And you could rewrite this as natural log of x plus 1 to the minus 1/2 plus natural log of x minus 1 to the 1/2. And that would be the natural log of, believe it or not, of x minus 1 to the 1/2 over x plus 1 to the 1/2. And you could do all sorts of different ways you wanted to write that. But you can solve it. That's the key. Okay. Now, obviously, the way I did it, you have to be very careful you don't make a stupid mistake like I was about to do 2 or 3 times there. Let me show you actually an easier way to do it. Okay? The book's going to show you this as well, but let's go back to our original one. Okay, I see people getting things together. We're getting close to out of time. It's what? Okay, well, we got 4 minutes, or 3 minutes. All right, so let's get that done. Let's go back up here, and rather than doing it this way, okay, I'm going to show you a slightly easier way to do it. Okay? All right. And here's what it is. And this, I almost don't like it, even though it's easier, because it doesn't feel right. It doesn't feel like you should be able to do this, but you can. If that was your original thing, I forgot one thing here. Okay. If that was your original expression there, here's what we do. Let's multiply both sides of the equation by x plus 1 times x minus 1. Okay? And over here, that's exactly the same thing, so that would give you a 1. Right? And over here, you would get a times x minus 1 plus b times x plus 1. Do you see when you multiply both sides of the equation by that least common denominator, which x plus 1 times x minus 1, that's what you would get, right? Now here's the part that doesn't feel right, but you could do it and it makes a lot of sense. I mean, it doesn't seem right. On the first one, let's plug in x equal 1. Now, why that to me feels really bad, because that's not even allowed. You can't have x equal 1 in that original form, but let's do it anyway and see what we get. Well, here you get 1, and here you get, when x equal 1, that goes to 0. So you have b, and if x equal 1, this would be 2b. Isn't that what we had to begin with? B is equal to 1/2. And then plug in x equal minus 1 to the original form. And this still is a 1 over here is equal to, and this would be a minus 2a, right? Because it's minus 1. What in the world was I doing there? It's not minus 1/2. Oh, wait. B is equal to minus 1. Where did I get the 1/2? I don't know. Minus 1. Plug that in, you get this, and when b is minus 1, that goes to 0, and you get a is equal to minus 1/2. That's a lot easier than the way I was doing it before. So that's what we're going to do from now on, the easy way. When we can. There still may be time you have to do systems of equations. If so, we'll do them. But for right now, we did it. And by the way, they got the same answer we did. Now so we'll pick up. Now the next statement they do, a rational function P over Q is called proper if the degree of P is less than the degree of Q. That's what I was saying before, so we've already done that. We'll start with those examples there and do those next time. Okay? So we'll talk about proper and improper rational expressions. There's not enough for you to do any homework exercises there yet, but we'll let that go for now. Okay? Good deal. We'll pick up there next time. See you Wednesday. All right, let me end screencast.